Hi, welcome back. So this is going to be quite a short video, but I just want to do a little bit of a deep dive into some additional notes on heuristics. Right, so we've already defined what a heuristic is. We've seen that they are just some rule of thumb, some estimate of the distance to go, but we have talked about some really important properties, that being the property of admissibility and the property of consistency. Both of these being extremely important for the behavior and effectiveness of our algorithms. But in this video, I just want to discuss some common heuristics that you're going to see, some natural intuitions of how you could try to come up with heuristic functions of your own to suit some form of problem, as well as just to discuss the value of different heuristics, vice versa, in combination, and things like this. So yeah, welcome to Notes on Heuristics. First, I want to dive into essentially the concepts of informedness and dominance. So let's just talk about any heuristic H1 and another heuristic H2. So we have two different heuristics. They're giving us different numbers. They're using some form of different metric or idea in order to generate a heuristic function, an estimate of the distance to go. So in this regard, our job is at some point to choose which of these two heuristics we want to use for our algorithms. Well, we know that the initial idea of heuristics, right, is it's meant to be informed. It's meant to be guiding our search towards the target in an effective manner. So in that regard, we refer to the informedness of a heuristic as essentially the value of the information it's providing. The estimate. In an ideal situation, we would love our estimates of the distance to go to be a perfect distance heuristic. Wouldn't it be great if it told us the true distance? In these situations, we can actually essentially remove the need for online search, right? If we already run a search algorithm, we find the real cost, we're storing those paths and we use those as heuristics. Well, this is the concept of what we're going to be calling compressed path databases, CPDs, and we're going to talk about that in a future video. But yeah, so in an ideal world, we can store all the perfect distances from any node n to any goal g. The issue with that is that the size of the data structure is going to be gigantic, right? Because you don't know where the start and goal will be in a given domain. We're going to have a series of problems, you never know which one you're going to get. So if you want to effectively pre-compute all of this information, well, you're going to have to store that in an all pairs distance table, right? So for all possible pairs, it's essentially like an n squared operation where n is the number of nodes in the entire map. Well, that's going to be a fair amount of work and a fair amount of storage. But all of this is to say that in an ideal world, we'd love to get the perfect distance. However, oftentimes we're talking about online search. We don't have time to exhaustively pre-compute the solutions to the entire domain. That is quite rare unless you're something like a video game developer, right? We have all the time in the world ahead of time to store these informations that you can speed up retrieval, essentially, of the information. Most of the time, though, we're interacting in a real-world situation. We're trying to adapt given our start and goal location, and we're searching as best as we can online with no pre-existing pre-computation available to us. So in these situations, what are we looking for then? Well, we want our heuristics to be informed. We want them to provide us with the best guess, the most information possible about the problem. So essentially, you would say something is more informed, right, if it gives you a better estimate. We're going to talk then about the concept of dominance, which is a stronger version of informedness. So a heuristic H1 dominates another heuristic H2 if and only if. The two F's here is like mathematical terminology for if and only if H1 of n is greater or equal to H2 of n for all n, right? So for every node in the graph, if it gives us a better heuristic value for all nodes, or at least equivalent, then why would we ever use H2? We would simply choose to use H1 in every single situation, and this is where the term of dominance comes in. If we can reason over the environment ahead of time and determine that one heuristic dominates another, well, amazing. We can essentially remove that other heuristic and we will always prefer and use the dominant one. Now, oftentimes the issue with that, of course, is that we don't have strict dominance. It's often quite you're unsure whether one heuristic will return a better value than another one. So we're going to have to play around, explore, experiment, and kind of get an intuition about how these heuristics kind of correspond to practical performance, right? The theoretical guarantees are always really, really important for understanding the underlying issues, but oftentimes it's practical performance that has to drive our decision making. If one heuristic does not perform well in say for example in sparse maps versus highly dense maps, well then maybe we have to start shifting the way we're trying to solve the problem. So all of this is just to say, if one heuristic is more informed than another one, well that is going to increase our performance. It's going to give a boost to performance. It means if our algorithm is more informed about where it wants to go, well we will have fewer node expansions and search will progress faster. But what I want to really hone in on here is a really awesome fact about heuristics, right? So before we've seen algorithms like A star are essentially, we're using this G of n plus H of n. What's important about H of n is that it does not overestimate the true distance, and that is also consistent, and that is both. But what is really cool here then is how do we pick this? Well, we can kind of pick this from any of them. Our H of n, we can define this function as any way that we want. And so a really interesting aspect of heuristics is that we can mix and match happily. So let's pretend I have a whole series of heuristics. I have H1, H2, H3, HV, whatever, right? We have some number of heuristics. Okay, if I were to ask you right now, which one of these would you prefer? The answer, obviously, it doesn't seem apparent. You immediately kind of respond, well, I don't know, of course. I don't know what the heuristics are. But let's reason over that. In the case that I have a whole series of heuristics that I know are both admissible and consistent, right? I've defined the heuristics in such a way that they have really nice properties. Well, it's actually as easy as if I define some meta-heuristic, h prime of n, is equal to the max of h1 of n, h2 of n, hv of n. I can simply max over them. We know that what we're looking for in a heuristic is to provide us with the best estimate, right? Okay, so let's think about what that means mathematically. We know the heuristics are admissible. It means they never overestimate the true distance. In that case, what we're looking for, the most informed heuristics, are the ones that give us the closest number to the optimal cost, right? So to do that, it's safe to just use a maximum over the possible heuristics we could have used. The one that has the biggest number is the best heuristic for the current node n. So that's a really, really interesting aspect of these heuristics. We're able to kind of like mix and match and create these meta heuristics where perhaps we could try, if the heuristics are fast to compute, we could try a few of them, pick the best one. And in that regard, let's talk about then some of the common attributes of heuristics. So we talked before about how you could try to spend a lot of pre-compute time to find these perfect distance tables. That's very expensive. What we often do with heuristics is we often want to define heuristics to be quick and fast to evaluate. So these heuristics are often very, very simple. And even these extremely simple ideas, right, we want the calculation of h of n to be extremely quick so that it can inform search, but it is not detracting from our actual ability and time to search over the nodes. So as long as they kind of fit this admissibility and consistency criteria that we need, we're often pretty happy as long as the heuristic's kind of guiding us, it's giving us a reasonable enough estimate. So yeah, one of the common ideas with heuristics is we want them to be fast to compute. Well, let's then talk about some of the most common heuristics that you'll see in the literature. Those being the Manhattan distance heuristic, the Octile distance heuristic, and the straight line distance heuristic. So these are, I think, the first three you usually look at when you start talking about heuristics, and they're all extremely easy and they make sense, and they come directly from the kind of common domains you're going to see. So imagine we have a grid, right, where you can only move in 4 connected space, right? It's only north, south, east, and west. We often call this and label this just as 4C. So if you're in a 4 connected grid map, one of the most obvious heuristics then, hey, how far away do I think I am from the goal? I'm just going to compute the vanilla grid distance, right? Hey, assuming there's no obstacles in the way, how far away am I? How many moves would I have to, how many cells would I have to move in order to get to the goal? Well, remember, it's important to not overestimate. We don't know if the actual path will have to take a detour or not, but we're happy to underestimate. Right? So, simple, let's just use grid distance. Well, the Manhattan distance heuristic is just the 4 connected grid distance. It's called the Manhattan heuristic because the city of Manhattan is often very grid-like, and this comes from the original notation in its history. Then another very common augmentation to a grid map domain is an 8 connected, an 8C grid map. So here not only can you move in the cardinal directions, but we can move northeast, right? Northeast, southeast, so forth. It's these diagonal adjacency rules. So in an 8 connected grid map, well, why don't we just again, and a very natural idea is, can we just measure the grid distance again? But this time the grid distance is diagonals plus number of straight moves. Well, that is where the octile distance heuristic comes into play. So it is simply just the number of grid cell movements required, including diagonals. Now, one standard thing to note about the octile distance and diagonal moves in general is that if we were to draw essentially the triangle, right? So our diagonal movement here between 2 grid cells, if we think about it, when you go diagonally, you could have instead gone straight and then straight again. So these have the costs of 1, and due to our high school Pythag, that means that the cost of the diagonal movement is traditionally given the cost of root 2. So when you're looking at your octile distance heuristic in an 8 connected grid map, it would be your number of diagonals is, hey, there was 4 diagonals, so it's 4 times square root 2, plus the number of straight moves, which is just, if there's 5 straight moves, it's plus 5. So that's pretty simple. Finally then, there's also the straight line distance, which is another really common one. This is actually just your Euclidean geometric distance between any 2 points. You draw your straight line, you calculate that distance using Pythag once again. Okay, so I want to then just walk through a very, very simple example where we look at the problem domains and we talk about, for each of these heuristics, in which domains are they admissible and consistent, right? So this will give us a better intuition of where and when can we mix and match, and when can we choose heuristics to use and in what kind of problems. So I'll speed run the obvious ones. So we've just defined that essentially the Manhattan is useful. It's defined for 4 connected grid maps, so believe it or not, it is admissible and consistent, and the same is true for the octile distance with an 8 connected grid map. Okay, so how about Manhattan in an 8 connected space? So I'm allowed diagonal moves. So I've drawn up a very small example here where we just have start and goal is only 2 steps away. It's 1 diagonal step and 1 straight step. Okay, so we're using the Manhattan distance. The Manhattan distance here is the 4 connected grid distance, so it's going to say, we think we are 1, 2, 3 steps away from the goal. Well, if you were to do the math, those 3 steps is an overestimate of the true cost. Diagonals, because of the triangle inequality, right, where we've just seen from consistency, the hypotenuse of a triangle, right, is smaller than the sum of the sides. So essentially root 2 is less than 2. What this means, that is, of course, because the true distance using a diagonal is shorter than doing these large steps, no, the Manhattan distance heuristic is both inadmissible and inconsistent in 8 connected domains. So if we continue then across to this domain here, I forgot to talk about this. This is road networks. So another really common one, this is essentially our graph analogy, right? So you have a series of connections. We don't know how many other nodes you can reach from each other one, but it will just be equal to the number of edges, right? The number of outgoing edges from each position. So road networks are much more scattered and relevant to the real world scenarios, right, where things can be connected in regions or not, but essentially we're just saying that the road network is just a big graph. So in these domains, I think it's quite easy to see, very similarly to the Manhattan distance being inadmissible for these 8 connected. If we put this onto a grid, you would see that taking the big straight steps is again going to be inadmissible. Let's move on then to the octile distance. This one's quite interesting now. In a 4-connected grid map, in a world where we're only allowed to take the long routes, well, instead this time we're returning the cost of the blue route. We're returning a smaller cost than the real cost. Well, interestingly enough, remember, all of this comes from the definition of admissibility and consistency. That means that the octile distance heuristic is admissible and consistent. It is strictly less informed in a 4-connected grid map than the Manhattan distance. The Manhattan distance will dominate the octile distance in this domain. So if we were to choose, yes, we would choose the Manhattan distance because it's going to provide us a better estimate, but nonetheless, this is the power of heuristics and the power of A-star search. In real-world problems, it can be extremely hard to come up with heuristics or to really actually estimate in a good way what the real distance will be. There could be a large, dense amount of walls and detours required. Well, it doesn't matter. As long as we have a heuristic that's admissible and consistent, it's meeting these properties, we're happy. The A-star algorithm will return a complete, it is complete, and it will always return the optimal solution, even using the octile distance heuristic. So that is an extremely powerful guarantee. Of course, we've already checked this one off. The final one then is in road networks, the octile distance. This is interesting, right? So you're saying only these 45-degree diagonals are used for the cost. Well, that is perhaps an overestimate still, right? Because we don't know what the angle of all of these roads may actually be at. They could be at any angle, essentially, right? It's a real-world problem. Well, then, unfortunately, we may be inadmissible. We would not be able to use the octile distance heuristic in this domain. So finally, then, this kind of brings us back to the straight line distance. So this is just our straight Euclidean distance. Draw a straight line, find the distance. Well, similar logic to the octile. This also underestimates, which means, sure, it's less informed, but we're happy. We would be happy to use it. It would still work, and A-star would maintain the guarantees that we want it to. This is, again, similar to the 8-connected grid map, and then I forgot to kind of do my full diagonal here. Well, the straight line distance does work on road networks because it works at any angle, right? You're actually able to find the real-world distance between those cities, between those points, by following the distance of the road. That has an asterisk, of course, that the cost of the edges is actually just the real-world distance. So if the road network was defined in terms of numbers for amount of minutes that it would take to drive, well, then the two costs aren't correlated, and this would not be true. So maybe I'll put a bit of an asterisk there. But in the case that the road network is defined in terms of edges having costs equal to distance, well, then we work. So all of this comes back again, right? Wow, strangely, the straight line distance here has checked all of our boxes. It is admissible and consistent in all 3 of the domains. So why wouldn't we just pick the straight line distance heuristic in every single problem? Well, it is again the idea of informedness. Despite the fact that it is applicable, and that makes it a very, very versatile and fast to compute heuristic that maybe you want to weave into your problem, it is not always the most informed. It is not guaranteed to give you a very accurate heuristic at all. And so because of that, no, you can never really unless there's this dominance property that you're actually able to observe and prove. So realistically then, you want to tailor your heuristics to the domain, to the type of problem you're going to solve. So this video has dealt with very, very simple heuristics and very, very simple problem domains. But we are often able to simplify, to abstract the world into these kinds of problems so that we can actually reasonably solve them and provide pretty good quality solutions that we could perhaps map back to real world problems and so forth. But these are extremely relevant to solving actual problems in the literature and to then translating back to the real world. So heuristics are here to stay. We're in the field of I've been calling this pathfinding fundamentals, but realistically everything I've talked about thus far is more in the world of just heuristic search itself. All of these are, all algorithms we're going to be seeing from here on out rather, are heuristic search algorithms such as A* and GBFS. They provide us with really powerful information. We leverage them. We try to design them to be better. We try to improve practical performance. We try to create interesting and cool new ways to reason over problem domains and come up with rules of thumb that can help us find goals quicker. And I think the really exciting part of all of this is that it is human ingenuity that's driving this field, right? It is humans reasoning over the world and coming up with potential ways and fun rules of thumb that we can apply to simplify the problem and to improve performance. So please stay with me as we start to see the impact of these heuristics. I'm going to do some visual explanations of all the algorithms we've seen and kind of show how A* performs differently, right, with different heuristics, and we can start to see how Informedness actually speeds up search. So please stick with me for that and see you in the next video. Thanks.